A number of years ago, some colleagues and I developed a new fisheries management instrument. It is still under development and it hasn't been implemented in the real world yet. We have presented its concept and we have been exploring and are still exploring how it might work. In this presentation I show some of these explorations, namely how it would work to manage mixed fisheries and ecosystem considerations, such as bycatch of vulnerable species, with one integrated system. Imagine you are a fisher. You fish in a mixed fishery and you catch an assemblage of 3 species, A, B and C. The catches are restricted by quotas. We are not living under the discard ban yet, so these are landings quotas. Each of these quotas require a different amount of effort to fish them up. Species A is soon fished up, but species B requires much more effort, and species C is intermediate. You are entitled to fish up all the quota, so you go on fishing until you have got all your fish of species B. But because they are caught as an assemblage in a mixed fisheries, this will mean you will overcatch species A and species C. You are still allowed to catch them, we are not yet living under the discard ban, but you have to discard them, because you are not allowed to land them. Now imagine you are a manager. You are confronted with overexploitation of stocks A and C and all these discards. So what do? You can use effort restriction and ensure that fishers have limited days at sea so that they can just catch species A. Or you can use catch quota and a discard ban, implying that the fisher will have to stop fishing as soon as he caught his quota of species A. Now imagine you are the fisher again. This is pretty annoying, because now you have to forego the catches of species B and C. Despite that you are legally entitled to fish up these quotas. That is why species A is called a choke species. It chokes the mixed fishery. At least that is what we assume to be the case under the unavoidable fixed mix paradigm. We would like to replace that paradigm with the spatial heterogeneity and targeting paradigm. This paradigm makes use of the fact that the catch or landings composition in a mixed fishery varies at a very fine local scale. Here, in the Irish otter trawl fishery, each of these tiny squares reflects the catch composition, or the landings composition. Here is one square magnified to have a close look. The proportions of each color reflect the proportions of these fish species at these locations. For example, green is haddock and red is cod. Now when you zoom in, you can see that at quite a fine spatial scale, note the 10 nautical miles bar, the catch composition can change from having quite a lot of purple but little orange, to a lot of orange but no purple. Our proposed new management instrument, we call it RTI, makes use of that spatial heterogeneity. Instead of catch or landings quotas or days at sea limitations, each fisher gets an allocation of, let's say, 200 RTIs. RTIs is what we call them. you can view them as fishing impact credits. In our system, this single currency of RTIs regulates fishing mortality on all 3 species in one go. So instead of 3 quotas, there's only 1. The fishers can fish when and where they want and land all catches, but they have to pay from their 200 RTIs according to a tariff map. The managers will set these tariffs according to the historical information and real-time information on the abundances of the 3 species, such that the fishing mortality is regulated to the respective species targets. So in red areas, for example, the choke species may be very abundant, and the fisher will spend 5 RTIs per day there and cannot go on there very long with only 200 per year. However, he can go to light orange or yellow areas where he pays only 1 RTI or 0.5 RTI per day and avoids the choke species but catches more of species B or C. And then he can go on much more days per year. We studied in the simulation model, an individual-based model, how this works. This diagram represents the model. It is an abstract model. It does not simulate a real region, like the North Sea or so. It's just a square of 10 by 10, with fictive abundances of the 3 species in each cell, giving rise to tariffs according to a rule. The rule makes sure that each of the tariffs, white, yellow, light orange, dark orange, red or gray for closed cells, is based on the abundances of the 3 species. Different rules are feasible. We simulate that the tariffs are updated in weekly time steps based on real-time e-log information from the fishers. And there is also a harvest control rule adapting on an annual timescale. That means that if the target F for any of the 3 species is overshot or undershot, the tariff thresholds are adapted. We ran simulations with traditional management and found that under effort management the fleet would have only 70 days at sea, resulting in being spot on with regards to F on species A, but in underexploitation of 50 and 33% respectively for species B and C. The same would happen under catch quotas. Under traditional landings quotas, the fishers would use 140 days and fish up all quotas, leading to 100% over quota catches of species A and 33% of species C. With our system, depending on what the fishers are targeting, they can fish up to 130 days at sea if they want to target species B. In total, there is only 4% of overcatching of species A, and only 12% and 6% respectively underexploitation of species B and C. So there is still a trade-off, a compromise between overexploitation and underexploitation, but not as strongly as with traditional management. So with these abstract simulations, we have shown that in essence the RTI management instrument is superior to effort management and catch and landings quotas, because it is able to use spatial heterogeneity and fine-tune the fishing opportunities so that each target can be approached much closer. The extent to which it works depends of course on the extent to which the 3 species have an uncorrelated spatial distribution. We ran several scenarios to explore how it works. For example, 3 cod-like species, or 2 cod-like species and 1 herring-like species, or simulations with 3 commercial species and a vulnerable ecosystem element, such as a vulnerable habitat or a vulnerable bycatch species. In these latter 2 cases, the target mortality rate for the vulnerable element was of course much lower than the target mortality rate for the commercial species. In each of these scenarios, we found qualitatively similar results. The RTI approach is being implemented in the AllRack software for e-logbooks so that it can be made operational. Thank you for listening.